is essentially the picture in the notes. So we have the center of the conic, at least if it's an ellipse or a hyperbola, where you normally talk about the concept of center. If the best you can, or the closest you can get to that, if it's a parabola, is to think of the center at the vertex, but you're thinking more of ellipse and hyperbola with these pictures. And so either looking there or looking here, you see the center, and then as you read to the right, you will have a focus, and it would be the focus if it's a parabola like down here, or it would be a focus if it's the ellipse or the hyperbola. And if you want to have it so it's focus and then curve and then directrix, reading left to right, you're thinking of this focus if it's an ellipse, you're thinking of this one if it, and this branch if it's the hyperbola, and you're thinking for your starting position of a parabola that's opening to the left with focus and then center at the vertex and then directrix. So you have this sequence. So then at the focus rather than at the center is where you take your origin if you're thinking either XY graphing or pole for polar coordinates. In that way, which we're taking as the standard position for representing the conic in polar form, we can get the relationships that we're going to work with here in just a second. So, starting with the pole here then, say, think of this as part of your curve, whichever it is. You have a point on the curve r theta, where r is from the pole, and theta, I'm taking the line here as my initial ray, and so then r cosine theta, if this is our origin, would be the distance here that's in the rose color, and I have a point P on the curve, a point F, which is my focus, a point D on this line that would be what I call the directrix. So the PD, theta D distance in green up here would be the same as this distance down here. So the distance from the pole, which is also the origin, over to the directrix is what I call K. We'll see later on today how you can relate K to what is called the eccentricity, E, and to the A, as we use it usually in either the ellipse or the hyperbola. The A is the distance from the center to the vertex. If you're like this, if it's the ellipse, or from center to vertex like this, or like that, if it's the hyperbola. But for the moment, let's just call this distance K, as the book does. So then K is R cosine theta plus P to D. And the concept called eccentricity relates the P to D distance to the R distance. Eccentricity, you can define it as the ratio of P to F, which is to say R, to P to D. And so what we have then down here is that PD plus R cosine theta is K, is this focus to directrix distance, but also PE times PD is PF, which in turn is R. So what you get then is that the P to D is K, this distance, minus R cosine theta. So the R, which is PF equals EPD, says R equals E times K minus R cosine theta. And so finally, if you solve for R in this equation, so you have R equals EK, where K is this far, and E is this eccentricity, which would be a number that you'd have for any particular curve. So your R then is this number minus the ER cosine theta. So you take this to the left, and you get this line, and then you can factor the R, and you get this line, and then if you solve for R, you get the standard form of the equation of the conic in polar coordinates. See, your variables are the angle and the R, and your parameter, a number that can change from curve to curve, but is a fixed number for that curve, is what you call the eccentricity. So if you're given a polar coordinate conic, and if you have coefficient 1 down here, then the absolute value of this coefficient is the eccentricity. And if you divided that eccentricity into whatever is your numerator, your quotient would be this K, which is from the focus to the directrix distance. So if you're actually given the formula for a conic in polar coordinates, then you can read what is its eccentricity and what finally is this distance we're calling K. So the denominator to read the eccentricity has to be in the form 1 here, plus or minus the coefficient, and you see you can rotate through an angle alpha by changing the theta into theta minus alpha. Because always, if you have a graph R equals F of theta, the same function of theta minus alpha is the original curve rotated through angle alpha, rotated counterclockwise if it's theta minus alpha. And that's what I've said here. So you can use some trig identities. Cosine theta minus pi over 2. Cosine of the difference of angles is the product of the cosines plus the product of the sines. Cosine pi over 2 is 0, sine pi over 2 is 1, so it's the same as sine theta. So if this becomes ek over 1 plus e sine theta, then what you've done, in fact, is you've imagined that you have this drawing, say, on a sheet of paper, and you have it attached with a pin at this point, say, to something like a bulletin board where you can pin things up and so on. Then you take hold of your figure here and you rotate it up like this 90 degrees. And in the handout that you have, just a second here. On the, turn the page, and if you look at the top picture, I have pole, and then I have the curve. You see I've rotated it through 90 degrees, and then the r is ek over 1 plus e sine theta, and then I have the directrix, which then would become a horizontal line, y equals k. Remember, the origin is at the pole, so if the distance from origin to directrix is k, then in this picture, as I have it here, the equation of this vertical line is x equal k, and then if you rotate it, like the top picture on the back, it's y equals k. So suppose you went counterclockwise through pi, so now you took hold of this and you went over to here, then cosine theta minus pi gives you cosine theta cosine pi, which is minus 1, sine theta sine pi, which is 0, so you get minus cosine theta, and you see the center picture where now your directrix, so that goes with this. I'm asking you to imagine with me that I have this entire picture on a sheet of paper with a pin into the bulletin board here, and that I have this line sticking out, so I have a handle and I can take hold of it. I've done this, okay? And so you got to rotate your mind 180 degrees. And then you see the directrix is off to the left, so it's x equal minus k. And then you have pole, and then you read left, pole, curve. The pole is at the focus, and these conic sections always open over the focus. For example, if it's like this, you have the focus and you have the curve opening over the focus. Or if you had been working from here, the curve opens over the focus, or here or here. And finally, if you rotated through 270 degrees, 3 pi over 2, your cosine would be 0, your sine is minus 1, so you have minus sine, and then you have the bottom picture on the page, and the directrix then is down here as a horizontal line, and that would be y equals minus k. So you could start with your conic section as any of the 4 pictures and use the corresponding formula. So you can say that r equals ek over 1 plus e sine theta is the equation of a conic in polar coordinates, just as well as saying this if you want to, and then you're starting out with a picture like the one on the top of the page, where the pole's here and the curve's up here and it's opening down over it and so on. So this is a matter somewhat of whose book you're in and whose class you're in. And when we look at the maple, you'll see that maple from one picture to another is not always consistent about what it's doing. In other words, they're not always starting out with this setup, but if they're not, it's one of these others. And the corresponding change either to sine or to cosine with a minus in front of the E, or a sine with the minus in front of the E. And they show the where they're putting their pole, and so you could tell which it is they're doing. So then looking at the top of page 3 of the notes here, you see I'm saying a polar equation of the form R equals EK 1 over 1 plus or minus E cosine, or EK 1 plus or minus E sine, represents a conic section with eccentricity E. And it's less than 1 if it's an ellipse, equals 1 if it's a parabola, and greater than 1 if it's a hyperbola. And there I have the 4 pictures side by side as you go down the page, another way to say it. So if you're looking then at what I have over here, I'm saying that the eccentricity is, there are 3 relationships that involve eccentricity, let's put it that way. And you can take any 2 of the 3 and get it to imply the third one. So they're all equivalent in that way, and that's what the work is about that's over on this panel. So in section 11.6, which we were working with last week, that's the conic sections in Cartesian coordinates. If you remember, that's what we talked about last Friday. We defined eccentricity as C over A, where if you have the center of your figure at some point, C is the distance to the focus or a focus, depending on whether you're talking parabola or ellipse or hyperbola, and A is the distance from the center to the vertex on your curve. So that's one definition. Notice that if you wanted to, you could multiply top and bottom by 2. This would certainly be true if this is. And so then 2C for a figure that is either an ellipse or a hyperbola, 2C is the distance between the foci, and 2A is the distance between the vertices. So you can think of it that your E is the ratio of these distances, if you want to think of it that way. Okay. Notice that if you're defining the parabola, the C is equal to the A, the E then is 1, equal numbers here. In other words, from the point on the curve to the focus is equal to the distance from the point on the curve, say, to the directrix. And so you'd see that kind of in my picture here. I have the parabola, and of course I haven't drawn it perfectly, but more or less the two distances in green should look sort of equal. Let's see, he is working with to look at the ellipse, we were working with this last week. The c square is a square minus b square, and so if you take the c over a, thinking of eccentricity, you have square root of a square minus b square over a, and this is certainly smaller than this is. The a is the same as square root of a square, whereas this is square root of a square minus something. So this has to be smaller than the square root of a square. So this, with a smaller numerator than denominator, has to be less than 1. And for the hyperbola, c square is a square plus b square. So reasoning in the same way I was here, thinking of this as the square root of a square, this is the square root of a square plus something. So that's more. And in other words, if I wanted to, I could have rewritten it so that I had a single square root sign, and I had a square minus b square over a square here, and had a square plus b square over a square here, all under a single square root sign. Maybe that would have been better. So you should see this is less than 1 and this is more. And so p to f is less than p to d, and in the hyperbola, p to f is more than p to d. And in this would be like an ellipse. I think this p to f looks a little shorter than this p to d, so on. Okay. So again, this picture, like the one under the screen there, this to here is r cosine theta. Center to here is the a, center to here is the c. Then in the brown, the a minus c, the blue minus the black here is this brown, which is p to f. If you're measuring it down here on this line, and the x is the distance from the center to the directrix, and x minus a would be this brown distance, brown colored distance, which is p to d. As I wrote, x minus a is pd, a minus c is pf, where I'm measuring everything from back here. And I have my pole again here, and point on the curve, so on. So the three things, the three statements that are equivalent in pairs are the E is C over A, or same as saying this distance is the same as that. The distance x from the center to the directrix is A over E, and the eccentricity is the ratio of PF to PD. This distance, the two green, this is the ratio of the two distances in green. In other words, E is PF over PD. So so what I'm doing here, if you notice, I have 3 red boxes. And so I'm taking 2 of the 3 statements and getting the 3rd one as my conclusion in the red box. And I'm doing it 3 different ways, because there are 3 ways that you can take 2 out of 3 things, you see. So if I begin with E equals C over A, which is our definition from last week when we were working with Cartesian coordinates, and also add in the distance x from the center to the directrix being A over E, then I can come out with the conclusion that E is this ratio, PF, this length to that one, PF to PD. So see how I do this. A equals itself, certainly that's true, A equals A. And then from the left-hand A, I take away C, and from the right-hand side, using this definition of eccentricity, which says C is AE, I write the C on the right-hand side as AE. And then what I do is if you notice the A that's here, I can multiply and divide by E. I'm just multiplying it by 1. So this A is rewritten itself E over E, and then the AE is there. So now I can factor in here. I can factor this E in the numerator, and so it's E, this A over this E minus that A. And that still equals A minus C. Okay, then I use that this A over E is X. See, that's one of the 3 statements involving eccentricity. The 3 are this one, and the one that the 2 together imply, which is this one down here. So I use now that this is X, so then A minus C is this E, and this is X minus A. So then solving for this E, that's right here, it's this A minus C over this X minus A. Okay, but A minus C, see, A is from here to there, and C is from here to there, so A minus C is this distance in here in brown, which is PF. So this numerator is PF, and the X minus A is this distance in brown, which is PD. So starting with this definition and this as a relationship and doing some algebra proves this relationship. Okay, so I'm going to do this same game twice more. This first time around, I've used this definition of E from last week and this relationship about how far from the center to the directrix. And with those 2, I can conclude then that E must be this ratio of distances. Okay. Next, what I'm going to do is begin with this ratio of distances being E, and use again that the X from center to directrix has to be A over E, and conclude this has to be true about eccentricity. See, that would be this over here. That's what I'm going to do now. And then finally, I'm going to do this one more time with E as these two ratios and conclude with those that the X has to be A over E. So you have three statements involving eccentricity, two of which are ratios, and the third of which is the center to directrix distance. And you can take any two of them and prove the third one. So that's what I'm in the process of doing, and I've started this. I've started with the E is C over A and this statement about the distance and proved this one. Go back to my papers here. Okay, so beginning with this, then the P to F again from the picture is the distance that I've marked here with the brown, so it's A minus C, and the P to D from the picture marked here in the brown is X minus A. Now I use X is A over E there, so sticking A over E there gives me this. See, this X has become that, and then this is all just copied. So then from this, if I multiply this denominator by the E, I have this E times that. So I need the arrow where it implies this E times this is A minus C. So multiply through distributive law. You have A minus AE is A minus C. So then the A subtracts off. So AE equals C, and E is C over A. So if you begin with this definition of eccentricity and use the relationship between this distance I'm calling X from the center and the A and the E, do algebra, you get this, which is my conclusion. Okay, one more time. This is the difference between training and education. Training, you just say, well, this is what it is, and do the problems. But see, you're being forced to really think through why do you have these, and so on. So you can somehow feel anointed, perhaps. Okay. So begin with E is this ratio of the two lines, again, these two distances, and also the ratio of the distance between the foci and the distance between the vertices, which is what the C over A really amounts to. Okay, so again, the X minus A from here, vertex to directrix, is your P to D, and so your P to D is PF over E, where your PF is A minus C, again, P to F. If you come down here along this line, P to F is the brown. So now you have this relationship involving the X minus A and the A minus C. So you can solve for X, take the A across, and get a common denominator. And C is AE from this, so put in the C, and then they cancel, and it leaves you X equals A over E, which I've written out like this. So if you assume E is this ratio of distances and C over A, then you can get that the distance from the center to here that I called X has to be A over E. If you're thinking especially of something like the Earth, then we have the center of our orbit, we have our the sun at one focus, and then if we're over here, we are closest to the sun. The Earth's orbit is actually much more circular than this picture. But so that the real drawing would have the two focal points very close together and to the center, but I've exaggerated. So if we are at the closest, if you're thinking that the sun is there, then that's called perihelion. The PERI is, I think actually is Greek and is close to or in the neighborhood of, and the helium is the Greek for sun, helios, and for example, the element helium was named because it was first discovered as a gas in the spectral analysis of the elements that are in the sun, and then later on it turned out they found a place in Texas where you actually get it in gas wells. But so closest to the sun would be here if the sun is at this focus, and at the greatest distance would be over here, which is aphelion. So notice then that we can get our hands on what these distances will be for a orbit in terms of the value of A and the value of the eccentricity. So once again, really it's the same drawing that you've seen twice. You have your center, you have your focus, and this distance C, which is AE from this, and then you have the distance we've called K if we were doing our formula for the conic section in terms of polar coordinates, EK, and so on. So focus to directrix is K. Then A is center to vertex. Then A over E is center to directrix. Notice that if E is C over A, and you put C over A there, then A over 1 over C over A is A squared over C. So the X is also A squared over C. So if you go back to here, the K is the X minus the C, so it's A over E minus C, which is EA. So you can factor the A, and it's 1 over E minus E, or it's A times 1 minus E squared over E. So then EK, which is this numerator, which we haven't really done anything with yet, is what you'd get if you multiplied here and there by E. So you'd cancel, and you have EK is A times 1 minus E squared. So we know from over here that the polar form of the conic is R is EK over 1 plus E cosine theta, if that's the starting position, and then more generally we can change the angle here. So then the EK is this, A times 1 minus E squared. So what I've proved here is that you can write the polar form of your conic in terms of what would be A, the distance from the center to the vertex, and the eccentricity. And you don't really deal with this distance K anymore. Okay, this is what proves to be what people do in astronomy. They, for an orbit, they get the eccentricity and what would be the distance from the center to the vertex. So then you can find out from this what would be the distance at perihelion, which is closest to the sun, or aphelion. So you see, if you take this, if your theta is 0, if you're thinking of theta as the angle right there, then theta is 0, you're here at perihelion. Cosine of 0 is 1, so then this denominator is just 1 plus E. And you notice you have a difference of squares here, so if you factor and cancel, you have A times 1 minus E. So the distance then, R, from the sun to the Earth here at perihelion would be whatever is the major axis length times 1 minus the eccentricity. And at pi, your cosine pi is minus 1, so you have 1 plus E times minus 1, so you have 1 minus E, and you factor into here. And so now the R from focus to there is the major axis length times 1 plus E. Well, it might seem as though there isn't that much difference, but for the Earth's orbit, the Earth's eccentricity, the difference is about 5 million kilometers, which is a long way to walk in the winter. So even for something that's nearly a circular orbit, if you're talking the kinds of distances you have in astronomy, 1 plus E and 1 minus E times your major axis length, semi-major axis, center to vertex length, can be quite a big number. So what we'll do, well, let's look at our maple pictures a little bit. Not sure. Second here. Maple that you got last week that starts out in 11.6, which is your conics in XY coordinates, and then partway through it changes to 11.7 and the conics in polar. So if you look on the back, if you have the right set of maple, you see things that are in polar coordinates. Okay, so who's here doesn't have this?
I have it.
You don't have it, I have some more. The second sheet of paper, and we pick up with the polar coordinates. So you notice that the pole is located at one focus. So then you look at, I have polar plot, 1 over 1 plus 1 cosine t. Okay, so that should tell you your denominator is in the form 1 plus your something times your conic, and your coefficient on the cosine is just 1, so your eccentricity is 1, so you should think parabola. And you see the red there, you see if you do polar plots, you get the polar coordinate graph paper, and then your graph is appears on that as if you had made a drawing on polar coordinate graph paper. So you see that you have just really a portion of a parabola. That's because of my choice of limits on the angle. I'm using t for the angle because it's easier than typing out theta and so on. So I do the problem over again on the next page, and you see I've gone to find something that looks a little more like a parabola probably, and a bigger scale. And then I've done it again, and without the polar plot, I've said coords equal polar. So then you get the graph without the background of the polar coordinate graph paper. And then finally, if you want this to really look like a parabola, I have minus 5 pi over 6 to 5 pi over 6, and turn the page, and you see that the thing looks really like a sideways opening parabola. Where we are with this. And you see the problem that you have with the parabola is that it extends off to infinity. So you can't just say 0 to 2 pi, because essentially, this being a left-facing parabola, as you've seen, when you would cross pi, the angle theta equal pi, so that you turn through the 180 degrees, you're trying to chase the thing out to infinity. And so all you'll get then is the horizontal line on what amounts to the negative x-axis. So you have to limit your angle in some way because of that. It's the same as trying to draw a graph in XY form and cross a vertical asymptote. If you try to do, say, 1 over x, and you try to do implicit plot y equals 1 over x, x equals minus 1 to 1, unless you limit the y, you're just going to get a picture of the y-axis because it's got the vertical asymptote. So you have to limit your y. Okay. Now, you don't get into such difficulties with a ellipse because it's a finite figure. So, problem 38, you notice my comment. Ellipses are more user-friendly. Note that the pole is at the right-hand focus, and so plot 6 over 2 plus cosine t. Now, you don't know at first that that's an ellipse, because remember I've been telling you that to identify the coefficient here as E, this has to be a 1. When the denominator has the form 1 plus or minus E cosine theta minus alpha, that's the coefficient. So to recognize what you have, you'd have to divide top and bottom by 2. So it's the same as 3 over 1 plus a half cosine. So now you see the eccentricity is a half, and therefore that it's an ellipse. Okay. As far as getting Maple to draw the graph, you don't have to change the formula, but to know that the thing's an ellipse, you do. And you see what it is. It's an ellipse, and you see where they show you where they're taking the origin, and therefore the pole. It's at the right-hand focus. So it's basically as though your pole is here, you see, and then you could think of it that it's this figure. Or if you prefer, you could think of it that I took hold of this and did that with it, like that. So they're thinking of it that they're starting with the right hand, the pole at what would be like the right hand focus. Then with the next one, again, to recognize what you have, since your leading term in the denominator is a 10, you'd have to divide by the 10, and top and bottom, so then you'd have minus a half as your coefficient on the cosine, so that's ellipse again. And you see it's like the EK over 1 minus a half cosine t, and so therefore you have your pole at the, you can either think of it, you have the pole at the left-hand focus, or that you have the pole at the right-hand focus and you rotated it around 180 degrees. So then we have another parabola, and this time we have to stay away from 0 because it's a right-hand opening parabola, as you see. And so if you were at 0 for your angle, you'd be going off to infinity to the right. And then you get an ellipse again, and you see now it's as though you've rotated this figure so that you're in the position where the pole is at the focus that's up at the top of the picture, and then and you notice that the formula involves the sign. So this is the form EK over 1 plus E sine of t, which would be what you get if you took the thing as I have it set up here and rotated through 90 degrees, and then you'd have a sine in your formula. And then you have done the same kind of thing with a parabola in 42, and in 43 again is a parabola, and then the last one is the ellipse finally where you have minus the sign. So if you thought of it the way that I was talking in my notes, I've rotated through 3 pi over 2. So Maple is very nice when you're doing something like this because it will draw the picture for you, but they correspond to taking the basic figure as I have in today's class and rotating it through whatever number of degrees it might be. Well, I think this is enough of this